Hi everyone, and welcome back to another Signals and Systems video. The topic of today's video is filtering of sinusoids using linear time invariant systems. So let's get started. So today's problem is, suppose that we have a sinusoid, meaning x of t is equal to cosine 2 pi t, that goes into an LTI system. And our question is, what comes out? What's y of t? And we're also given that we know that the system frequency response looks like this. It has a magnitude that's equal to 1/2 between minus 10 pi and 10 pi, and a phase that's equal to minus 3 omega. So it's a linear phase, varies linearly with omega, and it's has a negative slope. So the slope of this line is minus 3. So it really is an ideal low-pass filter because it passes things between minus 10 pi and 10 pi with a gain of 1/2 and rejects things outside that band. By reject, I mean the frequency response is 0 outside that band, and it has this linear phase characteristic. So there are a couple of different ways that we could think of to solve for the output of this system, and we're going to see a few of those in this video. So let's take a look at one way to solve the problem. And in this way, what we'll do is we'll say, well, we can rewrite x of t using Euler's formula as 1/2 e to the j 2 pi t plus 1/2 e to the minus j 2 pi t. And in this way, we've written the input as a sum of two eigenfunctions. I'm going to abbreviate eigenfunctions here. And so these two things are eigenfunctions, and they have different frequencies. One has a frequency of positive 2 pi, and the other has a frequency of negative 2 pi. And we know that when we have an eigenfunction that goes in, the output is simply a scaled version of that eigenfunction, and the scaling factor is the frequency response for the frequency of the complex exponential. So we could write the output as y of t is equal to h of 2 pi, j 2 pi, times 1/2 e to the j 2 pi t, plus h of minus j 2 pi, times 1/2 e to the minus j 2 pi t. So all we've done here is scaled the eigenfunction by the value of the frequency response at the frequency of the eigenfunction. Okay, so that means we just have to read the frequency response off at a couple different points. And the 2 points we have to read it at are at 2 pi, so 2 pi would be somewhere in here. So we look at what it is there, and 2 pi on this graph is somewhere, say, here. That's 2 pi. And so we get a phase of that value. And then we also have to, so first we do that here. Let me just change my pen back. So we could calculate that the output would be, well, h of j 2 pi. Well, that's going to be equal to 1/2 e to the minus j 3 times 2 pi, because that's what the phase is there. Remember, h of j 2 pi is a complex number. It has a magnitude here and a phase here. So we rewrite that as it'll be 1/2 e to the minus j 3 times 2 pi times 1/2 e to the j 2 pi t. So these two terms here represent the scaling factor, and this was the input eigenfunction. We can write the other term in a similar way. Now we're just looking at the value of the frequency response at minus 2 pi. Well, minus 2 pi is over here. So that's going to have a magnitude of 1/2, and then the phase will be a positive phase now. It'll be minus 3 times minus 2 pi. So we can write that as follows. It will be 1/2, that's the magnitude, e to the minus j 3 times the value of omega. Well, the value of omega is minus 2 pi here. And then we multiply by 1/2 e to the minus j 2 pi t. So all we've done is use the eigenfunction property and read the value of the frequency response off these two graphs, off the magnitude and the phase graphs. So now we can reduce this a little bit. So let's change pages. So all I've done here is rewrite the expression that I had on the previous page, and now I'm just going to combine the complex exponential terms to simplify it a little bit. So I'm going to also pull a 1/2 out front. So I'm going to have 1/2 times 1/2 e to the j 2 pi t minus 6 pi. This minus 6 pi just comes from this term here. And then the other piece will be plus 1/2 e to the minus j 2 pi. Whoops. Got to get the parentheses in the right place. It'll be e to the minus j 2 pi t minus 6 pi. So now we can see that this looks like e to the plus j something plus 1/2 e to the minus j something, where the two somethings are exactly the same. So this looks like cosine, right? Particularly since we have a 1/2 term there. So we can simplify this to be 1/2 cosine of 2 pi t minus 6 pi. Or we could write this another way, 1/2 cosine of 2 pi times the quantity t minus 3. If we multiply that through, we can easily see that we get the same expression here that we had here. So the input was a cosine with a frequency of 2 pi, and the output is also a cosine with a frequency of 2 pi, but it's been scaled by a factor of 1/2 and delayed by a factor of 3. So we could have, and all we used to solve for this was the eigenfunction property. Now we could have just jumped right to this solution if we go back and take a look at the form of the frequency response. So we notice in this frequency response here that it is symmetric. So the magnitude is an even function, meaning that I have the same magnitude at 2 pi that I have at minus 2 pi. And the phase is an odd function, meaning that I have the opposite phase at 2 pi that I have at minus 2 pi. So magnitude was even, the phase was odd. And whenever I have this case, I'm going to have the situation that I have that in this problem, which is that I'm going to be able to combine back this overall solution to get a cosine of the same frequency, but just phase shifted. And it's phase shifted by the amount of the phase at the positive frequency. And that indeed is what we got, because the phase at 2 pi is minus 6 pi, so it was phase shifted by that amount. We get the same cosine out, but it's multiplied by a factor of 1/2 because that's what the frequency response of the filter did. It had a magnitude of 1/2 at 2 pi, and it had a phase of minus 6 pi at the frequency of 2 pi. So whenever we have this symmetry, so the key here was if we have a conjugate, well, specifically, if we have a conjugate symmetric frequency response, h of j omega, then if we put in cosine of omega naught t to an LTI system, what will come out will be that cosine scaled by the magnitude of the frequency response at omega naught, and phase shifted by the phase of the frequency response at omega naught, which is exactly what we have here, right? It's equal to, right, h of j omega naught was a half, and the phase at j omega naught, in our case omega naught was 2 pi, was minus 6 pi. And so whenever we have a conjugate symmetric frequency response, we can know that we'll be able to combine the two eigenfunctions that we split the cosine into back into two eigenfunctions that now represent a phase-shifted cosine. And the other thing to point out here is that a conjugate symmetric h of j omega means that we have a real impulse response h of t. Okay, so that's something else to know. Now, I didn't actually have to know this fact to solve this problem. I could always split the input up into two eigenfunctions, scale those eigenfunctions by the frequency response, and then add them back together. And I got the exact right answer. But if I know a little bit more about the symmetry of the frequency response, and I remember what that does, then I know I'll always be able to simplify back into a form like this, and so I can leap directly to this answer if I want to. Now, there is another way that we could have solved this problem, namely we could have used the Fourier transform. So let's see how we could do that. Okay, so this was the frequency response of the system that we started off with, and we remember that the input to the system was cosine 2 pi t. So we know what the Fourier transform of the cosine looks like. The cosine has simply two impulses with area pi at the positive and negative frequencies. So this is what the Fourier transform of the input signal was, right? Because the input signal is cosine 2 pi t, and this is what the Fourier transform of cosine 2 pi t looks like. That's a transform pair we discussed in class, and we derive it using the Fourier series. So now what do? If we know the transform of the input and we know the frequency response, we can easily calculate the transform of the output. The transform of the output, y of j omega, of an LTI system is just going to be h of j omega times x of j omega. Well, we have x of j omega here. We also have h of j omega. We have its magnitude and we have its phase, right? So h of j omega is a complex entity, and so we have to specify it as magnitude and phase, or real and imaginary part. Okay, so all we're going to do is basically end up multiplying this by h of j omega. And if we do that, well, now we're multiplying two impulses by another function. Well, if we multiply impulses by anything, we just get the impulses back, and they're scaled by the value of the other function. So y of j omega could easily be sketched as just two impulses, one at minus 2 pi and one at plus 2 pi. But now they have an area of pi times the value of the frequency response at the location of the impulse. So this one is pi times h of j 2 omega, and this one here will be pi times h of minus j 2 pi. Let me rewrite that a little more clearly here. So this will be pi h of minus j 2 pi. Okay, so all I've done is multiplied these two impulses by the value of the frequency response at the location of those impulses, because that's what happens when we multiply anything by an impulse. We just we just scale the impulses by the value of the function we're multiplying by. Okay, Well, in our case here, we can see, well, the magnitude of both of these two things is going to be the same. It'll just be a half. We figured that out before. And the phase of these things, this one will have a phase of minus 6 pi, and this one will have a phase of plus 6 pi. But overall, it's basically the phase is e to the minus j3 omega. So what we're really saying is that y of j omega could be written as follows for this particular signal. We could write it as, well, it will be equal to x of j omega times the magnitude of h, 1/2, times the phase, which will be e to the minus j3 omega, right? That is the magnitude and phase. This right here is h of j omega. Well, first of all, we can see if we've multiplied a transform, all we're doing is multiplying the transform by a half. Well, by linearity, that is just going to mean that x of t is scaled by a half. And if we multiply by the time delay theorem, if we multiply something by e to the minus j3 omega, then we're delaying it in time by a factor of 3. So we could, using linearity and the time delay property, we could easily show that y of t has to be 1/2 x of t minus 3. Okay, and that's just from linearity and the time delay property that we can apply given that we have this particular system. Well, we know what x of t was, so we can rewrite this as 1/2 cosine of 2 pi quantity t minus 3, which is exactly the same expression that we got before. So we can say, you know, this is the same as we got before. And what have we done here? Well, we used the Fourier transform. So we used the Fourier transform and a couple Fourier transform properties that we could apply because this h of j omega for this particular system takes on a very simple form. Okay, now if we didn't remember linearity or we didn't remember the time delay property, we could just go about taking the inverse transform of this function just directly using the inverse Fourier transform definition. So let's see how to do that. So I've recopied what I had before. Y of j omega is just going to be this, right? It'll be these two impulses, and they have areas. The first one has an area of pi times a half times e to the minus j3 times minus 2 pi. Again, this is just the frequency response, and the pi was from the original x of j omega transform. And this is the same thing over here. Now we're just evaluating the frequency response at 2 pi instead of at minus 2 pi. So then, to solve this, we just plug into the inverse transform equation. Here's the inverse transform equation. It's 1 over 2 pi, the integral from minus infinity to plus infinity of y of j omega e to the plus j omega t d omega. Okay, we can substitute in. We have two impulses here. So it'll be 1 over 2 pi, the integral from minus infinity to plus infinity of, right, we have pi times a half e to the plus j 6 pi delta of omega plus 2 pi e to the j omega t d omega. Plus, right, we have a second integral, 1 over 2 pi, integral from minus infinity. Actually, let me write this on the next line. Plus 1 over 2 pi, the integral from minus infinity to plus infinity, pi times 1/2 e to the minus j 6 pi delta of omega minus 2 pi e to the j omega t d omega. Now we're just integrating two impulses. Impulses are easy to integrate. If you've forgotten how to do that, you can watch the earlier video on doing that. All we do is, this is just scale factor stuff. That can pull out front. Then to evaluate the integral, we're just, well, let's rewrite it, pulling the scale factors out front. So pulling this out front, whoops, didn't mean to do that. We have pi 1/2 e, okay? So pulling these scale factors out, well, the pi's clearly are going to cancel. We're going to be left with 1/4 e to the j 6 pi. And then so that all pulled out front. Now we're just going to evaluate the integral of delta of omega plus 2 pi e to the j omega t, which all we do then is just evaluate this at omega is equal to minus 2 pi. And so we get e to the minus j 2 pi t. And then we get similar terms over on the next one. We get 1/4 e to the minus j 6 pi e to the plus j 2 pi t. And what you'll notice is this is exactly the same expression as we've gotten before, and so we could easily reduce this to 1/2 cosine of 2 pi t minus 6 pi, or 1/2 cosine 2 pi t minus 3. Okay, this is exactly the same answer that we've gotten previously, so we can put a check mark there. So what have we done here? We've solved the same problem, basically 3 different ways. One way we just used the eigenfunction property. The next way we used the Fourier transform and a few Fourier transform theorems. And then the final way, we just used the straight out Fourier transform and got the final answer using the inverse transform. We get the same exact answer any of the ways that we do it, and this method can, any of these methods will work to solve the problem. So that concludes our video. Hopefully you found it useful to watch, and if you want more information about this class, you can check out these various websites. Thanks for watching.